Hey team, I decided to record this video to go over some of the data with you and how to work with the Excel file to create your posters. And what we'll do is we'll go through what is there, and then we'll look at how to make graphs, and then we'll look at how to play around with the statistics. The statistics are already there, so you can just use those, but I also thought you might want to play around with them a little bit. I know statistics and math are scary, but I think you'll enjoy it. Um, I didn't do all this work. I did it with the help of Claude, which is an AI, which is very good at like statistical and programming stuff. So Claude helped me create all of these files so that we could get them pumped out pretty quickly for you. So let's go ahead and look at one of these Excel files, and I'll just pick one. Let me open it up. What do we got? Okay, hold on one second. Share this file. Let's do. Okay, so I guess we're looking at the bees, the apidae, and so we got. I got a ginger ale and a cup of tea, so I'm just gonna switch between those. So first, what you're gonna. So this is basically what we did is I downloaded the data from iNaturalist, which you've used iNaturalist. So this is the data on two transects. A transect is a line, a geographic line. So from Times Square going north up to Westchester, so a north transect, that's from like Times Square where it's high urban out to Westchester where it's pretty rural, about 60 kilometers. And then from Times Square east along an eastern transect going out to the edge of Queens, also 60 kilometers. And then we had, yeah, you can't just be a line, you have to have like a corridor, like a hallway, like how wide is the path. And so then along that transect, we looked at a 5 kilometer width, and then we broke it into every 5 kilometers. So looked at like species diversity or species richness every 5 kilometers in a basically a 5 by 5 kilometer square, and then the next 5 by 5 kilometer square running from Times Square out to Eastern Queens and from Times Square up to Westchester in the north. So a northern transect, an eastern transect, both 60 kilometers, both 5 kilometers wide, both broken into 5 kilometer sections all along the way, along the path. So when you do that, this is the kind of data you get. You just get like a mass amount of raw data. You don't have to know this. I mean, this is like you can look at this and just so it's got observed, time zone, who is the user who uploaded it, what's their login, what's their name if it's there, when was this created, what's the quality grade. We only used research quality data so that you can also use like other data like that's like you're not sure about the species, but we only used research quality data. And then where's the URL for it, etc. Captive culminated, I'm not sure what that is. O authorization application, I don't know what that is. Um, Place guess, where is it placed? Central Park. Latitude, longitude, we used latitude and longitude to create these transects. And then positional accuracy is basically like, how accurate was the position. Um, all the way over to the scientific name, so Bombus grisioculus, and then the common name, which is or the species guess, brown-belted bumblebee, common name, brown-belted bumblebee. What taxon is it? Insecta, that's the class, the big, and then what's the taxon ID? These are other things that are used internally to iNaturalist. So this is all the raw data. There's a lot of it, which is good. Just along those transects, there were um, 10,133, well, 32 minus the titles, 10,132 observations. So that's a pretty good sample size to do this kind of analysis. So what you're going to find on here is first just the raw data, which again, that's just for you to kind of check it out, not for you to really do much with. And I cleaned it. I took out all the stuff that had missing missing rows or missing data. I took out anything that looked funky. So that all was done. So it's all been what we call cleaned. So usually you have pure raw data and then you clean it, get rid of all the stuff that looks funky or that's missing a piece here or missing a piece of data there. And then you have your clean data. And that clean data is what you start to analyze. You don't analyze it when uh, and that can actually take a long time depending on how good your programming skills are, how good Claude's programming skills are. Claude's pretty fast at it. Um, so down here on the tabs, you can see that you have your raw data, then you have your graph data, statistical tests, stats data, transect, formula bar, and formula examples. We're just going to start out with the graphs. And I want you to play around making these graphs. I'm uploading a how-to guide to make these graphs for each one. So you'll have that, but they're pretty simple. If you've done graphs in Excel, it's fairly straightforward. You're going to make one chart, which is going to be uh, distance versus richness, Shannon-Simpson index. Another chart over here, another chart 3, chart 3B, chart 4. So you're going to make basically 5 charts and they'll be pretty quick. Um, I should say that the way the data that we're analyzing is if we look at these, and also if you can't read these and you want to expand them, you can double click on the edge of this box up here at the top. And when you do that, it automatically fits to the data. So I'm just going to click on these and open it up so we can read it. So just click on the edge. Whenever you click on the edge, it fits the data to the left. But if you have a really long piece of data, it's going to stretch. So if we look at what's in here, that's too high. I can bring that back. So you can adjust the columns up here. This is chart 1, species richness by distance. Now, species richness is calculated just as number of species you saw in that box. So I can actually draw on here. So let's move over here. So let's say we have our 2 transects. We have a transect going north-south from Times Square, and then we have a transect going east-west, going east out to Queens, and we have these broken into 5-kilometer boxes, right? So it's 5 kilometers wide and 5 kilometers. That's not very accurate drawing there, but within each of these, you can calculate the number of species. And that's going to be your species richness. So if you have 100 species, that's your richness in there. That's going to be kind of like your raw number, your basic count. And that's going to be up here, species richness. So all of these numbers are how many species were counted in each of those boxes at 0 to 5 kilometers, 5 to 10 kilometers, 10 to 15. It's better, instead of using these numbers here, like the 0 to 5, 5 to 10, to put it on a graph on an x-axis you just want to have one number. So instead of doing 0 to 5, 5 to 10, 10 to 15, we're just going to say 0, 5, 10, 15. So on your x-axis for these, you're going to be using for the first four, you're going to be using this column distance to start from start. And so this will be your x-axis here. And then you're going to do a y-axis with species richness, and that's just going to be the basic count. But there's two other metrics that ecologists use. The Shannon Diversity Index. So the Shannon Diversity is it's actually over on this tab. So on tab 5 under formula examples, it shows you how Shannon Diversity Index and the Simpson Diversity Index are calculated, which is what ecologists typically use. And basically it kind of helps kind of figure out like what's going on. So the Simpson Diversity Index is here, and it's basically just 1 minus the sum, here's the formula right here, of the percent for all species squared. So for example, here we have the percent, and here's the percent in this column, basically percent like index, PI. Doesn't matter what we call it, but we're calling it PI. But this PI is 0.3787. So this one's 0.2077. This one's 0.2018. So if we wanted to do this, for an example, we would do, oh man, so this is an arrow saying, here's an example. We would do 1 minus, oh, let's do that. The sum of 0.3787 squared plus, that's what sum means, right? So it's basically 0.207077 squared plus 0.2018 squared. Sorry, I just have to check on something real quick with my kid. This is where you can take a pause. And when you add all these up, one thing you're going to realize is that whenever you square a decimal number, it actually gets smaller. So what you're doing is basically the, the smaller these numbers are, they're going to get even smaller. And the smaller they are, you're going to get like tiny, tiny. So the more of these there are, because they're a percentage, the smaller they're going to be. So if you have like 100 species, then those percentages are going to be very small, like 0.02, 0.03. So then you're going to square them, get even smaller. And basically, the more diversity for the Simpson index, the more diversity equals closer to 1. So if you get 1, that means it is as diverse as it could possibly be. If you get 0 on the Simpson diversity index, that is not diverse at all. It's basically just one species, right? Because like that would just be one, the percentage would be 100% or one, and then one squared is one, so one minus one is zero. So basically, if you get a zero, that means there's only one species. If you get if you get a zero, that means there's one species. If you get a one, that means there's many, many species, and it's very equally distributed. So the closer you get to one, the more diverse on the Simpson index. So sorry, guys. I just had my kid's appointment here. The other one that's just as common, and I think was developed first, is the Shannon Diversity Index. And the Shannon Diversity Index is basically on a scale from 0 to, high, but usually kind of around 5. And it's basically this, here's the formula. So it's the sum of, I'm sorry, the negative sum of the percent index or the percentage times the natural log of the percent index. And whenever you take, this is back to your logs, right? If you take a logarithm, like log of a decimal, like 0.2, is going to equal a negative number. We can actually find out what that is. You can just do, um, oh no, where's my, I don't want to draw anymore. So we can even check here. We can go equals log 0.2, and that's going to give you negative 0.69897. So it's a negative number. So that's why you have your negative over here is to make the final result positive. So that's going to be negative 0.69. So we know that that's negative. That's 0.69. So whenever you have a logarithm in here, you're going to get a negative number. So you need to like uh, uh, multiply that by another negative to get a final positive result. And what you're doing here is basically just taking the raw percent index. So this is sort of the raw percent index um, times basically how small it is. And these two combined are basically giving you a scale that is easier to interpret. So the way it works is if it's about zero, if the final number is like 0 to 1.5, that's low diversity. If it's, so this is both like the percentage, but also the number of species total. Um, and if it's around 2.5 to 3, somewhere there, that's medium diversity. And if it's so I would say maybe this is actually 0 to 2.5, that's low diversity. 2.5 to 3, that's medium, and anything greater than 3, so greater than 3 equals high diversity. If you get like a number like 4 or 5, that's really high diversity. So that's the Shannon diversity index. So there's three things. There's the raw sort of count, like number of species. There's the Simpson diversity, which is 0 to 1, with 1 being the most diverse. And then there's the Shannon diversity index with uh, 0 to like, 4 or 5, with 4 or 5 being on the pretty high side of diversity. And on this table, you've got your numbers here, and you can basically just play around with them. They're already calculated down here, but you can actually just calculate these, and there's instructions, a guide to like creating them. But this is just so you see how the formula works for the diversity indexes and can play around with them a little bit. Let's erase this. So I say that because when we look at the other file, what we'll see is that well, it always takes so much more time to erase than it takes to. So when we go back to the graph data, oh, I gotta erase this too. What you'll see is that I apologize. I feel like I'm just like got a lot of pauses in this video, but it's good. It gives some time to process. What you'll see is that you have your distance from the start. This is going to be your x-axis, your horizontal axis. And then you have your basic species richness, so like just count of number of species. But then your Shannon diversity index, remember, which goes to 0 to like 4 or 5. And it looks like these ones are kind of on the low side. And then your Simpson diversity, which goes to 0 to 1. And then you also have your total observations, just how many times these were observed. So, you know, in this box, you had 4,236 observations, but only 25 species were cited over and over again. So when you create a graph, you're going to want to create a graph with this on the x-axis and one of these on the y-axis. And to create a graph, you just go to Insert up here. So that's Insert. And for the first 4 graphs, you're just going to do a scatter plot. And just click on a scatter plot and choose the one with a line. And it's going to give you a lot of stuff in there. And you're going to right click on the middle, right click, and go to select data. And then just get rid of all this stuff. Remove, 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 all gone. And now you're going to add your series. A series is a relationship, an X and Y relationship. So you're going to go to add series, and it's going to say, what's your series name? Click on that and pick your series name, probably going to be the title for that column. So we're going to do species richness. And then click back down here, open it up, and it's going to say, what's your X values? Well, I want those to be the distance from start. So I'm going to select all the way down to here, select these values. That's what I want on the x-axis. Then what's on the y-axis? Now, when you do the y-axis, make sure you get rid of this little 1 in brackets. Otherwise, it'll throw off your data. So backspace over that, and then click on the arrow, and then select species richness, which is the title we picked, all the way down. And then hit OK. And then OK again. And now you've got a nice graph with species richness on the y-axis along the transect of kilometers. Pretty good. Now, if you go up here in this area, there's all sorts of things to play with. You can change your colors. Uh, you can do this palette, whatever you want. You can do different layouts. So you can do this layout, this layout, this layout, whatever you think makes sense or what you like. Da 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 da. You can also add a title. You can add an axis title, like let's add a vertical title. Let's add um, a horizontal title, and then you can just type in here. So this is distance kilometers, something like that. Oh, don't hit that. And so you can basically just really, you can add error bars, you can add um, grid lines, legend, do it as, whatever you want to this graph. You can add, you can also right click on it and go to format chart area. And here you can add a border. Now I like a border, so I always recommend putting a border on it. And that color might probably be black. Now you've got a border on it. Um, Probably don't want to do a fill, that would be weird. You can add shadows, also weird, probably size, properties, that might be helpful. Text options. You've got like, you can add text to this, and you can also edit this title to whatever you want. Species, richness, like that. You've got like a ton of options to play around with. If you want to, when you find a graph that like you want to put in your poster, you just right click on it and go to save as picture. And then you can save it as either a JPEG or a GIF or a PNG. I prefer JPEGs or PNGs, honestly, for the posters. It usually works better. Um, uh, the TIFFs are actually the best for visual quality, but sometimes they take up a lot of memory. They're a little bit difficult to work with. Um, so you're gonna create some graphs, and you're gonna like on this one for species, you can do it for species richness, then create another one for Shannon diversity, another one for Simpson diversity. You can also right click on these axes and format the axis. You can actually change the maximum and the minimum, change the units. Like you can do all sorts of stuff to mess around with it. Um, Down here, you're going to do the same thing. So actually, I'm going to delete that. Down here, you're going to do the same thing. But in this one, for chart 2, you have your top 5 species that were found along that transect. So here, that's Bombus impatiens, Bombus griseoculus, Apis mellifera, Xylocopa virginica, and Bombus immaculatus. And those are down here. So these are the data that you're going to use. So when it says like, add series, this is going to be the title. And then you're going to just select these, but you're still going to use this distance from start for your x-axis, right? So keep with this x-axis. And then actually it's down here as well. So you can just use it down here and then use these as your y-axis. You could probably put all of these on the same graph, just add different series. So you could insert a chart, then add one series for this, add another series for this, add another series for this, and have all of these on the same chart. You could probably add these on the same chart, but because these, like the Simpson, only goes 0 to 1, and the diversity goes up to, the diversity species richness goes up to like 26, you'd have the scales are really wrong, so you can't really put them on the same chart. They would just look too weird. The one would be all smashed up. You wouldn't see anything. But these are all on the same scale. They're all the same numbers, just for different species. So you could actually do a different line for each of these. And then you have distance uh, versus north versus east. So basically, your species richness, which is just these numbers here, but basically for east versus north. So you would graph this on your x-axis and this on your y, and then also this on your y. Just add 2 series. And these would be the titles for each series up here. And then you also have distance uh, versus east and north. And these ones are 1.64, 1.8. These must be Shannon diversity indices. So these are the Shannon diversity indices if you want to plot Shannon diversity indices also for each of the axes. And then, but those are all going to be scatter plots. So the same type of graph. You can also compare just the overall uh, species richness, Shannon diversity, and Simpson index. The two big ones just on the north-south. And for this, you want to use a bar chart. So I would go to Insert and pick a bar chart up here, like this, and then do the same thing. Right click on it, go to Select Data, just go ahead and remove that, add a series. What's your series name? Series name is going to be, well, if we're doing species richness, we're going to go all the way up to species richness, like that. And then what are my values? They're going to be these ones for species richness. And then I'm going to hit OK. And for the bar chart, it doesn't allow you to pick the X axis data right off the bat. You have to go to horizontal axis label, click edit, and then it says, what's your range? And you go, my range is east and north. Those are the two range. Those are the ones that are right here, right across. So now you can hit OK, and you've got this like species richness. So going east to north, you've got much more species. I'm sorry, going from Times Square east, you have much more richness than from Times Square north. So nice little chart. And so again, those are the 5 charts. They shouldn't take long to make once you get the hang of it. Play around with it a little bit and create some graphs for your poster. The other tabs are statistical. So you have statistical tests. These have already been done for you. And basically, there are 3 tests we did together. By we, I mean Claude and I. We did a correlation. Correlation test is one of the most basic tests you can possibly do. A correlation test is just, are these data moving in the same direction at the same time? So, for example, if you have a bunch of data like this, like these dots, and you draw a circle, it's going to look kind of like an ellipse. And the reason it kind of looks like an ellipse is because some of these data are kind of moving in the same, like you could almost draw a line through the middle and see that they're correlated. And if they're really correlated, then you would see something like this, like a very tight ellipse. If they're not correlated at all, like there's no correlation, you would see basically a circle, right? You can't really draw, you could draw a line anywhere here. Who knows? You're just making stuff up. So correlation is sort of like how elliptical are the data? How much are they kind of running in the same direction? So are the data on the y-axis moving at the same rate as the data on the x-axis? It's a very simple statistic. Basically, it gives you a correlation from 0 to 1. 1 is perfect correlation. So if you have 1, that's basically a line. That is a perfectly correlated. That's a correlation of 1. So correlation equals 1. Over here with like a circle, correlation equals 0. And uh, here are the correlation values. If it's negative, that means that it's actually going this direction like this. So you're actually getting less as you go down, like less of the y-axis as you go down the x-axis. So this is a negative correlation. This is a positive correlation. This is a negative. So these are all negatively correlated, which means as you get away from the city, you're getting less diverse, which is interesting. And then we do a statistic to see if it's correlated. A statistic tests whether or not we can actually believe it. And we've already done that here. Basically, we look to see if the value, what's called a p-value, this is 0.05 or less. And if it is 0.05 or less, we call it significant. So these are not significant, but this one's significant, this one's significant. So this tells us that species richness is definitely getting less. And there's a correlation between the distance and the species richness, and is a negative. This says the same thing. Interestingly, when we did the Shannon, that didn't work, and we did the Simpson, that didn't work. So just the raw species richness count did have a correlation. That's interesting to kind of think about why. We can go into that. Something for like your results to talk about. Um, the next uh the next thing we did was linear regression. Oh, and there's two types of correlation, the Pearson correlation and the Spearman. So we did both of them. They're both pretty much the same answer, just they're calculated almost the same way. There's just, statisticians like to have a couple of options. So there's the Pearson, there's the Spearman, you've got options for your correlation. Some of it kind of works, one works better in different circumstances than the other. So, and then we did a linear regression. And a linear regression is basically just doing what we just did. So it's basically saying, okay, like you've got all these data points, and during the correlation, you kind of imagine this ellipse going around it. But what if you did try to put a line on it? It would look like this. And remember that the equation for a line is y equals m, that's the slope, times x. So there's the x-axis, x-axis here, y-axis here, plus or minus b, which is the intercept, whether or not the line shifts up or down. So if you add b, like if this is your y times mx, and you add b, it might move the line upwards. If you subtract b, it might move the line downwards. So you're not changing the slope, you're just changing whether or not the line goes up or down. So this is often called the intercept because it changes where the line intercepts with the y-axis. Um, And so when you do this, you basically do some calculations to find out what your slope is and what your intercept is, and you fit, it's called a regression, fit, it fits a line to your data to see, if how good this is. And then you can do a statistic to test your slope to see whether your slope is significantly different from zero. If your slope's zero, then there's no correlation, right? It's just basically just a circle. So we calculated if you uh, scroll up, uh, open this up. There's your interpretation. Where's our so parameter? So here's slope, negative. We got a negative slope, which means the line's going downwards. There's the intercept. Don't worry so much about the intercept. It's not usually that important. But the slope is interesting. And then the R squared is like the correlation coefficient. It tells you how good the fit is. The higher the R squared, the better the fit, the more the data fits that line. And then we did a p-value test to see whether the slope was significant. And again, if it's less than 0.05, it is. So this is significant. So this is a good result. You're actually showing that this has a negative slope and that uh, you can actually calculate, the how based on the distance, what your species richness is going to be. So the nice thing about putting the equation for a line is you can model your data, right? So with the correlation, okay, they're correlated, but if I go 10 kilometers out, how much less diversity do I get? Well, you don't know. But if you put a line on it, then you have the equation, so you can put a value of X that might not even exist, like 70 kilometers, 80 kilometers, and then see what your species richness would be. So once you put a line on it, you have this nice map that you can actually make predictions with. Um, Interestingly, you can actually put this on your graphs. So, and I know this is kind of a lot. I just want you to play around with it a little bit, and then we're going to meet. And after you meet, I want you to play around with it and get some questions, write down questions, and then we're going to meet and talk about your questions. But I want you to play with it first. So up here, I'll show you this nice thing. Let's create our graph. So let's go to insert. chart, and we're going to insert this chart, and it's always going to just fill it up with, you can select data. I mean, it's sometimes doesn't know what it's doing. What happened to this chart? This chart, it's all messed up. You can actually just select this just to get it going, insert chart. Yeah, it looks weird. I mean, this is what happens if you put them all on the same scale. You can see that your species richness is up here. It looks all weird. And we're gonna right click, select data, remove everything, and then add a new series. And that new series, we're gonna pick the title, and we're gonna do species. Let's do species richness again. And then let's pick our X values. And that's gonna be our distance from the start. And then let's make sure we get rid of that one with the brackets. And they try to do some automatic helpful stuff, but it's not always helpful. And then do species richness. And then click OK. And then OK. And now you can right click on this line, right click on the data line, and do add trend line. And it does the regression for you. It adds a regression line. And now you can also get on here and do, yeah, display the equation and display the R squared. And so now you can, and I'll move this around a little bit so you can see it, but now you can actually see your equation. So you can actually now predict species richness beyond the data to 70 kilometers, 80 kilometers using this line. Just put in like 70 kilometers in the X and get out the Y, because you've got the line based on this data. And the regression is this is the correlation, the R squared. And it should match approximately what we did with the calculation. Sometimes the way Excel or software calculates it might have some rounding errors, like errors that come in when you get like lots of decimal places. So it's not unusual if it's off by like, a point or something like that, but should be pretty close. So you can do some really cool stuff just with like this basic Excel stuff. Um, and then the last one is just a t-test. And we covered this in class. I know some of you might have missed that, but for all statistical tests, what you're doing is basically doing that bell curve, right? So you're like, here's my data from one sample. Here's my data from another sample, and you're basically creating like a percentage normal curve, and then you're trying to see how much they overlap. And down here, we're doing a t-test, which is basically a simple test between two populations. And we're doing basically I'm sorry, that's bad. We're doing basically north versus east transects for species richness, Shannon diversity, and Simpson diversity. And you can see here the t-test results. And then you can see the p-value for each one. And none of these are significant for this. So basically, even though the bar chart shows there's more diversity, like more species richness on the eastern axis, it's actually this test is saying that that's just kind of a trick of our eyes. There's actually not. But it still doesn't mean it's not interesting and we can't talk about it and kind of think about like, what it would take to get us to significance, something like that. So that's your statistical tests on this tab. So we've done graph data, statistical tests, formula examples, and then if you want to practice your own stats, um, there's a guide I'm going to send you as well that has the like how to do these stats. And you can practice on this tab with stats data, and you can also practice over here on the stats transect data. So these are both tabs with practice data. Well, it's your real data, but it's where you can actually practice doing the statistics and the calculations if you want to practice t-tests or correlations, etc. And the guide shows you how to do that. Um, you For some of these, you'll have to go to your data tab and go over here to data analysis. And this will give you all these options. Like, do you want to do an ANOVA? Do you want to do a correlation, which we just did? Do you want to do a t-test like this? If you don't see this data analysis button, you need to add it into your Excel sheet. So you go to File, go down to Options, go to Add-ins, and go to Analysis Toolpack, and then click OK, and then close your program and restart it. If you still don't see it, then you need to come back here and do Excel add-ins go, and then make sure that it's checked. Okay. And then it should show up. So first you have to add it in, probably shut your Excel file down and restart it. So you could probably do that at the beginning before you do anything. Um, and then if it's still not showing, go back and make sure it's clicked in that example. And then just make sure you're saving a lot. So make sure you're saving every couple of minutes, 5 minutes, so that if something goes wrong and your computer crashes, you don't lose everything, which is terrible. And go ahead and like play around with the statistics, play around with the graphs, and just like, enjoy it. I find data analysis incredibly fun. Um, and to me, it's like actually one of the most fun parts of science is sitting down with an Excel file and just going through it and sort of checking to see what about this? What if we do this? What if I graph it this way? What if I graph it that way? Um, to me, that's like a really fun way to sit down with a cup of coffee and spend some time. Uh, especially since it's your data, it's your species that you're looking at, and then make some graphs, practice making some graphs, write down a bunch of questions that you have, and we're going to set up a meeting and like probably next week, or the week after. And depending, because I want to give you enough time to kind of play with it. So it's already going to be Thursday tomorrow. So maybe not next week, but the week after, I'll have meetings with everyone, and that will be enough time for you to play with this data and have some like real questions. And then we'll have a meeting and go over all your questions and troubleshoot if you're like having difficulty with like getting, and also just if you're really having difficulty and you're stuck, email me so that you're not just stuck for like a week and a half. Like try to make as much progress where you feel good about your graphs, you feel good about not maybe understanding the stats, but like just you feel good about sort of like understanding the most basic parts of them. And you have questions, but like, they're not basic questions that you could get answered by ChatGPT or something like that. Like I want that hour, that we spend together to really count. So probably not next week, but the week after. And then I think we'll be in really good shape for you to like finish up your poster, and uh we'll have it printed by easily by the I think it's like mid-February deadline. So I think we're in very good shape. Um and also, your poster would probably benefit from maybe one picture of your neighborhood or something like that, where you could talk about how in your neighborhood there's, you know, these trees or there's not these trees and why that might affect species diversity or species richness. Like, are there a lot of gardens in your neighborhood? Are there trees? Are there places where bees or birds could go? If you're on turtles, like, are there waterways? Like, so I think like just thinking through this a little bit and even adding a personal picture is always good. So um, all right, well, good luck and email me if you have questions, and I will see you all soon. All right.